talk to you today about deploying optimized deep learning pipelines. So a bit about me. I'm an O'Reilly author. I maintain a few open source projects, and I help companies build and deploy machine learning. So for those, as many of you know, if it's in PowerPoint, it's AI. If it's for coders, it's machine learning, and I do the latter, hopefully. So I started out, doing mainly Java, but slowly moved over to a lot of the Python world over the years, and now I help mainly on kind of the MLOps buzzword. That's always kind of been my main focus, and hopefully that explains today's talk. If you want to reach me, I'm on GitHub, Twitter, and LinkedIn at @GibsonCCC. So things we build, like I said, deep learning for J. It's a way of importing models and running them in production. If for some reason you use Java or the big data world, then we're also present there with Apache Spark, Android, among other things. And we also have quite a few other projects. Come find us at community.conduit.ai. So now what I want to do first is get into the problem definition. So optimization obviously means many things to different people, especially in the deep learning world. You could be optimizing a function, you could be tuning your model and making it more accurate. So I just want to define what this talk is and who it's for. So in this talk, when we say performance, will not mean evaluation metrics. So no F1 scores, no accuracy, nothing like that. Instead, we'll be focused, and optimization also does not mean optimization algorithms. So if any of you in the deep learning world, you're minimizing a loss function, you're using stochastic gradient descent, or any of those types of algorithms, this performance will also not mean anything to do with loss functions. We will also not be covering bias and generalization. So again, these are all aspects of a model to consider when building and deploying models. And these are usually at the forefront of a data scientist's mind when they're building a model. How do I generalize it? How do I make it more accurate? How do I make sure that it's going to work in the real world? This talk is targeted kind of at software engineers and people who, need, maybe you have a requirement to build a model that's not just, running on your laptop in Python. Maybe you need something more than that. So we'll focus on things like latency, throughput, examples per second. For those of you that maybe just train models and are kind of just curious about this kind of topic, this topic might help you understand the mechanics of training a model faster. So if you want to know more about any of these kinds of problems, maybe you're developing transformer models and you're looking to reduce your training time, and maybe you don't have 26 GPUs or TPUs to throw at your problem. Just making your models more efficient may help your training time as well as your deployment. So some acknowledgements. A lot of vendors tend to oversell the need for some of their software. I want to just acknowledge a few things. Most people aren't deploying deep learning models. Most of you are probably just using XGBoost. That's okay. Certain big size models are useful for certain things, and especially in NLP and computer vision. So not everyone needs performance optimization, and you probably don't have a 4 trillion sized model that you need to deploy. Most people don't. Accuracy, data quality, and bias are just as important as throughput. When you think about the aspects of kind of this MLOps buzzword that you hear about, if you're not familiar with it, MLOps is machine learning operations. It means operating models in production, making sure that you kind of maintain them like you do code. So in this case, data changes over time, behavior changes over time, and often you need to track these changes. And so models are not just something you train once, they're something that you train continuously. And so there's a lot of tools nowadays, kind of trying to bring more discipline to the machine learning workflow that isn't just Jupyter Notebook 1, Jupyter Notebook 2, et cetera, as some of you may be familiar with. So those things are just as important, but not the focus of this talk. So also, again, some of the techniques discussed here can be used for increasing the, kind of the throughput of models, making sure that you can train on higher batch sizes, making sure that your models train faster. You might reduce, if you only have one GPU or, just a CPU, any reduction in training time is welcome. But this is mainly for people looking to somehow optimize deployment of their models. And so that will mainly focus on inference. So if you're not familiar, inference is when you use a model. So, when you call predict, when you call output, depending on which framework you're used to. If you're using PyTorch, you're used to the idea of calling, passing data into a function and calling model like as a function. But either way, some form of prediction is the focus of this talk. So, to summarize, there's different MLOps categories. There's labeling and data quality. So when you talk about labeling, you mean, how do you label data at scale? Labeling itself is a hard problem, and I feel like a lot of companies and tools are being built and shared to label data in different domains. For example, in computer vision, you might highlight bounding boxes. You might, if you're doing video, you might be labeling video streams, like, from timestamp 5 to 10, a bike shows up. That's a typical thing people do. If you're labeling time series, you may be labeling anomalies, like, oh, you may be doing, a price prediction in the markets. That's something that people do. It's hard. It's not common, but, people aren't very good at it sometimes, but there it is. So, you generally, depending on the domain, labeling can be hard. If you're an NLP, there's a lot of great tools out there, like Prodigy is a great example from the Spacey guys, if you're familiar with that NLP framework. And so what you're doing is you're labeling bounds of text. So that's one aspect. And again, data quality. If you have noisy data, you may be focused on data set curate. Figuring out different ways to balance your data set better. That's again a whole discipline. So each of these things kind of deserves its own tool, its own workflow, and brings its own complexities. Then there's just the normal deploying models. So that's kind of the main focus for us in this case. So that could be setting up a model as a REST API, but generally it's just a way of saying I'm going to let an application like a mobile app or a web page benefit from the results of a model. The simplest thing could be for inference could just be you have an image, you have a file upload web page you go to, you click upload image, and it prints out some cat or dog as a label. That's a fairly, I think it's a fairly decent hello world example a lot of people do when they're first attempting to build models. Packaging. So how to deploy your ML pipeline. So we cover aspects of this as well, just because it's so important to know what hardware am I running on. Am I running on a GPU? Am I running on a CPU? Maybe I'm running on a Raspberry Pi. So then there's just, how do I install it? How do I make sure that the right the right native libraries are there? So for example, if you're say you have a hybrid project on a Raspberry Pi, you need to know the basics, like the Raspberry Pi is an ARM chip. It's not an Intel chip. So if I build a model on an Intel chip, how do I run it on an ARM chip? Again, it could be GPUs. So you need to know which version of CUDA am I running on. What is my framework that I'm using to build and execute models support? How do I install all that? A lot of people may use Docker, just Docker for that. The requirements vary. Big companies typically will have all sorts of different ways they might require packaging of their models. Some companies may be big, Java shops. Some, and so you can't even run Python in production. Or you could just be using the model yourself. Like when you deploy to production, and this is the way what a lot of people do. You're a data scientist. You are the consumer of your own models. So as long as it works for you, it doesn't really matter. So you might just hook up your experiment tracking software like MLflow. Weights and biases is pretty popular nowadays. You set all that up, and all you need is a REST API, and you're benefiting from your own results, and you don't really need to integrate with the software team. So you may be deploying the model in a mobile app. So that there's and so how do you distribute, say, an APK and that's an Android archive for distributing applications. How do you distribute a model with that? Do you download it? I mean, so there's all sorts of considerations when thinking about how to package your ML pipeline for actual real world use where, you know, your company, they told you to build a model and they're actually benefiting from the results of your model. You know, you could be improving the user experience, it could be anything, but packaging your model, in different scenarios is always important. And again, as I kind of alluded to before, experiment tracking, just sharing your results. You know, you don't want to, for example, if you train a model and you want to, for example, you add some new data to it, and it turns out maybe your model isn't performing as well as you thought. What do? So this kind of just gives you an idea on what to expect for, the end-to-end ML workflow. So what a lot of people will do is they'll combine all these tools together to build something valuable. So this talk, just so we understand, is mainly for the inference part, but everything is equally as important. Hopefully that kind of gives people at least a decent introduction to MLOps, some of the different things to consider, and where this talk kind of belongs. So from here on out, we'll kind of get into ways of improving model inference, making them more efficient, and this will include all ML pipelines. So when we talk about ML pipelines, we mean data input as well. So this could be something simple as minimizing the overhead of interacting with a model via HTTP. So if you've ever used requests or some other Python library for interacting with a REST API, then you may just want to do something basic like use WebSockets. Make sure that your server, your client is executing on a you're close to your model, so you have minimal latency. There's lots of things to think about there. But in general, when we talk about ML pipelines, we mean data input, we mean data output, and we mean model execution. So generally, the bottleneck is in the simple things. The first thing you should look at is just, again, Occam's razor, so to speak. If you're looking for bottlenecks, just look for the basics first. Like, is my data format efficient? Am I batching my data correctly? So when I say batching data, I mean, for example, you have 5 images, if you're doing images, 5 images at a time. If you're doing a CSV, you don't want to send a small CSV, like for example, like just say iris, for example, the iris data set with 4 columns. You don't want to just send 1 row at a time and invoke 100 requests on your model. Instead, you send 150 at a time, the whole data set, because it's small. Then you get the results back at once and you kind of benefit from, if you're familiar with the terms in NumPy, it's called a vectorized output. So vectorized output is where you're saying, I'm going to batch, I'm going to send so many things at a time and maximize the compute, kind of running on the server. So this is pretty common. You figure out the optimal batch size. The batch size in this case is like, what's the max I can handle? What's the most efficient that I can send and benefit from the results? Batching is also important in, just say, GPUs, for example, because if you're just sending one thing at a time, it's very slow, and the overhead of sending, 1 image to your GPU means that you're not really benefiting from it because you're not maximizing the amount of data that your GPU can handle, like your GPU RAM. You always want to maximize what we call utilization. It's a very common thing. This is applicable in training as well. When you train a model, again, you don't want to do it one at a time. There's trade-offs of model accuracy and generalization per batch, where just say you have, generally what you want is, multiple examples fitting one, if you're doing classification of one label per mini batch. So that way your updates generalize better. So there's always trade-offs to how you input data into your neural network or into your machine learning model. Okay. So what we're going to talk about is just a term I'll call deep learning operations. So again, most models probably do not need, and machine learning pipelines do not need, all the tools I'm going to talk about today. Like, one thing is like deep learning compilers, which I'll get into, which are ways of saying I have a model and I need to make it run and optimized on particular hardware and those kinds of things. So we're going to call that subset of tools deep learning operations. So what are the typical situations that you actually may need this? Like, I mentioned that most of the time people probably don't need this. And even for computer vision, you may not. But there are, I would say big, a few common scenarios that we're seeing nowadays. One is computer vision on mobile devices. So you may have a smartphone app, and it may take a picture of something, and it could just be to say help you with shopping. Take a picture of something on a shelf and identify what's the price of that. And so something will run on the phone. Why do we run on the phone, by the way? Why do we run around a Raspberry Pi or what have you? It's so we don't send data to the cloud. It could be for privacy reasons, and it could be, depending on the kind of hardware you have on the phone, it could be for performance reasons. There's a lot of what I'll call specialized chips that are especially running on mobile phones. Like I think Google just announced like their Tensor chip and the Google Pixel 6, for example. You have smaller devices like the Jetson Nano, which run, they only have 4 gigs of RAM, but it does have a GPU in it, and so it's going to be faster for deploying in at the edge. So when I say the edge here, I mean a small computer running machine learning locally, so it doesn't just call out to a server. It's not for everything, but I think it is applicable. So if as I mentioned though, you also may just fire them out to a big server of GPUs. Really depends on your use case, what you may do, but either way, computer vision is fairly common. The models are big. Convolutions are expensive. So a convolution, for those that are not familiar, you're mixing and matching, an image and then some neural, and superimposing that on some neural networks. It's basically a fancier matrix multiply with more than 2 dimensions. So that operation is expensive, and typically what you need specialized compute for. So, and it's also memory intensive. The other one that you see, I think, a lot more hype around, is NLP. NLP, I think, is kind of going through its renaissance right now. I think for the last 3 or 4 years, we've been talking about BERT, transformers. Those have been fairly big, and as of late, GPT, and their variants, all those have transformers as their core. So transformers are notorious for being computationally intensive, requiring lots of parameters. And unfortunately, we haven't, we're exploring ways to make them more efficient, but largely, even if you do shrink them down somehow, they're still computationally intensive. But that's what's kind of pushing the results. That's what's kind of pushing the leading edge in machine learning model accuracy. So those are increasing in production usage as well. And maybe just large CPU models. Maybe you only have Xeons to play with. Maybe you have something from Intel, and so you have to make something as fast as you can just running on the CPU, depending on your constraints. So either way, you're probably running something fairly expensive. So those are the 2 main situations that I see where there's actually real reason to want to do this, as well as just a compelling reason to not just go with XGBoost. So you probably do XGBoost for most things, but then for NLP and computer vision, you're probably using, you're probably git cloning something from Hugging Face or Google, and then fine-tuning it on your model. So if you're not familiar with fine-tuning, it's basically taking a model that was trained on, a bunch of data that maybe more data than you generally would have, and you're repurposing it. You're saying, well, this thing is good at understanding what cats and dogs are, so maybe I'll teach my model to understand lions now. Even though it wasn't trained for that, it probably has fairly good pattern detection for that. So that's called fine-tuning or transfer learning. Hopefully that makes sense. So typically you repurpose these big models, and then after that you want to deploy them somewhere. So again, when I say deploy, I mean set it up on a server and actually in a production setting. Like it's being used in a product. Like there's a separate team that's not you, your modeling team, a software engineering team that actually benefits from these things. And so those things, those models again require specialized infrastructure, specialized, maybe specialized hardware. Again, you may be using GPUs, TPUs. There's also like alternative chips. There's a lot of things like GraphCore is one I can think of that you kind of you may also be running. And again, it's kind of targeting this more specialized compute. So problem size. So again, I kind of mentioned these things are big. So how big? How big should they be for each use case? Well, so computer vision models are big enough that they need to be shrunk down. Like Raspberry Pi, the 4B only has at max 8 gigs of RAM. The Jetson Nano again has 4 gigs of RAM. Most phones don't have that much RAM either. So there's all sorts of things that need to be shrunk down. I won't cover it again, but just to review, NLP models are always increasing in size, and I don't see that ending anytime soon. There's kind of incentives to make the models bigger right now, because a lot of the companies kind of doing this research and building these big models also have a specialized hardware. So there's not a lot of incentive to make them more efficient right now, at least until more independent institutions kind of pull through and maybe optimize these models somehow. And in general, models, require optimization in order to run in a way, that makes sense for the business. So if you have a business requirement to run the model as cheaply as possible, then anything you can do to make the model more efficient is always better for you. So constraints are generally RAM and throughput. GPUs and all these other specialized devices don't have that much memory. So the more, so generally the devices that have more throughput, maybe specialized vector compute, don't have as much RAM. That's improving, but still the status quo is, the model's getting bigger. There's never enough RAM. And sometimes, depending on the model you have, you may invoke something called model parallelism. So that's when you shard a model across multiple GPUs or what have you. So there's all sorts of ways to scale out and train models and run them in production. If you have 4 trillion, I think I read an article, there was like, the next GPT-4 will be 4 trillion parameters or something, because why not? That's probably not running on a single GPU. There's no way. So you typically need to set up specialized infrastructure for just running those kinds of models. Again, as stated earlier, most people don't have those problems, but as hardware gets better, as we need more data for these kinds of problems, then this will become commodity eventually. And so just being aware of these things, I think, will help. And the more efficient something is, the more we can do with existing hardware as well. So beyond that, compute throughput, CPUs are slower, they have more RAM, they're easier to interact with, but in general, they're always going to be slower. So business trade-offs, cost, more compute is more expensive. Price and performance is key. So if you have a model, it needs to run in a constrained environment, then you're going to figure out the best way to kind of fit within budget. That's not something a lot of people think about. Instead, people just kind of build models, then they end up being too big. So what do you do in that situation? SLAs, high quality of service, is important. So what do we mean by high quality of service? Generally, we mean that the prediction doesn't take so long that it doesn't affect the user experience. Is the baseline for you. And then as well, when you're building models, accurate, unbiased, and fast models are key depending on the use case. So now I'll get into the components of an ML pipeline. So starting off, input pre-processing. So data needs to be transformed before it can be used. So that's one aspect. So there's a lot of different ways you can do that. One thing I'll call out is Apache Arrow. It's an in-memory columnar format that underpins a lot of the storage infrastructure we use today. So if you have a pandas data frame, you can actually convert it to Arrow and then send it to Spark, and there will be no. And since Spark already natively understands Arrow, there's no copy of the data. That improves performance by a lot. There's a lot of blog posts out on this, but it's just like one example of where where efficient conversion of data makes your whole pipeline more efficient, not just your machine learning model, like feeding data from your input into something like XGBoost. And usually fast transforms are an afterthought. It's not something you really think about. Unless your model is prohibitively slow during training, you don't really try to optimize that too much. But during production, if you go from training on lots of data at once to needing to have something that's like reliably have some reliable throughput, then you want to optimize your transforms where possible. So how might you do that? You could make the your data transforms in another language. Your production languages like something Java Java based like Spark or Flink, or even Go. Either way, you're going to pre-process your data somehow. You're going to convert it to a NumPy array, and then you're going to feed it through your model. So the faster that conversion or vectorization process happens, the better. In your models, so of course you're going to have your actual model, which is your keras, your TensorFlow, your ONNX, your PyTorch, or whatever sort of model you might be using. So again, when we think about ML pipelines, we're thinking about the complete thing, not just the model. Sometimes people only think about the model, but they don't think about all the other stuff involved. The latency of setting up, like a pub sub service, the necessary requirements of making sure that your data is batched properly. All those considerations we kind of discussed earlier. So when we say the ML pipeline, we mean the whole thing. So many of the, one of the problems today is that many of the tools I'll mention later are actually not, are only focused on models. So there's initiatives to try to capture the whole ML pipeline, but it's still like a lot of the time you're still writing one-off code in order to actually process all your data. So in this case, there's still room for, ways for you to make your stuff more efficient just with better coding practices. Again, this depends on your use case. So the best way to think about ETL and data pipelines, raw data needs to be converted to NumPy arrays. Data can come from anywhere. So, I already kind of covered this earlier. You have all sorts of data sources, databases, S3 buckets, over the web with REST and streams. Data can have different formats. So I covered Arrow already, but there's also GRPC, which is fairly common now, especially with Kubernetes. The way all the services in Kubernetes talk, GRPC is everywhere. And obviously JSON is something I think most people are familiar with in some form. In summary, data movement and storage is its own set of problems. A great example that we learned about, we did all the way back in 2009 or something like that was Hadoop. So Hadoop, what it was built on was data locality. Running your compute distributed, as well as your storage distributed. So everything is what we call fault tolerant, which means if a server dies, then you can, your data isn't corrupt. So what you want to do is you basically build your jobs such that your compute happens close to the data. So a scheduler figures out the best way to say, okay, let me run on this batch of data, let me run this compute over here and then click the result over here. That's called a map, and then you reduce. Reduce means, okay, let me collect all the results, and that could be a sum operation, could be a mean, it could be whatever, it could just be a count. But anyway, that was the whole idea behind MapReduce. So run the compute as close to your data as possible. That's commodity nowadays. A lot of things do that out of the box, but it's still good to understand that basic thing whenever you're asking, why is my pipeline slow? What happened? You always want to dissect parts of it wherever possible. So decomposition in optimizing ML pipelines is always going to be key. So models. So for those not familiar, models can be stored in all sorts of different formats. So when you think of a model in the deep learning sense, generally you have your graph, which is something like you have your input, you have you might have like an X and a Y, and then you might have an add, and then those are expressed in terms of nodes and edges. So you have a graph, and then you get a result out the end. So that needs to be defined somehow. So there's different binary formats for doing that. One is hdf5, which is the keras format. There's protobuf, which is used by TensorFlow and ONNX, and then there's just normal pickle, which is used by PyTorch and Python. And I think most of you will be familiar with pickle. Model files are a mix of configuration and parameters. So typically, as I mentioned, these models can be huge, trillions of parameters, or even just even a few million parameters still ends up being, could easily be a couple gigs. So these protobuf files are notorious for being fairly large. If you think about it, when you build a model and say you're doing keras applications and you're fine tuning a model, it takes a while to download. That's because there's parameters baked in. So I like the way keras does their file format, for example. They actually have the keras JSON, which is just the definition of the graph, and then all the other parameters. So it doesn't couple all the massive blob of parameters, like the big matrices for the representing the model weights, as well as the configuration. They kind of allow you to separate it potentially, which is kind of nice. By the way, those things are fairly large. You need to store those somewhere. And so when you have an ML pipeline and a model is loaded, you load a model into memory, and that can take a bit. And the bigger that model is, the longer it takes to load. The more memory it takes, especially when it's uncompressed. A lot of these models parameters actually may be compressed as well in these binary file formats. So just understanding that this exists, you don't have to understand the nuts and bolts what's protobuf? You may be just asking that. Just knowing that exists and that it's big can be very helpful for just understanding, why is my model taking so long? Well, how big is it? You can actually see that on disk. Like, so if you ever call keras.save or what have you, you can actually see how big your model is. And generally, most of it is parameters. There could be other things as well. Model files may also contain like updater state, for example. So I covered optimizers at the beginning. You have like Adam, you have Adagrad, you have all this state around model that that you may save for a model. So you're actually saving that state whenever you save like a TensorFlow checkpoint, for example. So in this case, what do? What's in there? Like, so that when you load that, again, you have all that state. So what's that for? That's when you want to continue updating your model. So you want to kind of continue from where you left off. That's called a checkpoint. So there's all sorts of things to understand when thinking about how to store models and what's in there whenever you think about a model file. So so in summary, ML pipelines are not just models. ETL can vary. It could be your own custom code. It could be it could be an end-to-end thing, like so it's something TensorFlow tf.data does is they try to encompass the whole ML pipeline, and they try to make all that a TensorFlow graph. So that may work for you. There's also keras preprocessing layers. So some frameworks are starting to get into the idea of fusing ETL pipelines like preprocessing and models, but it's still not a very common process. And generally, the more specialized your data is, especially in NLP, the harder it is to kind of fuse all those things together. So you always end up generally having some custom code somewhere. So just being aware of that for your use case can also help in kind of increasing your throughput. And then again, something else you may store, like in something like weights and biases, MLflow, is metrics and experiments, which may be stored with a given model. So when you're serving a model, generally you're loading the whole pipeline. You run predict, and then you run some preprocessing, convert that to an ndarray, get your model out, and then that runs like predict, and then you get your result out. So all those things need to be stored. If you ever want to resume training your model, if you ever want to measure its accuracy, or if you ever just want to measure and compare models. So the key performance considerations: faster ETL, better data interchange, better in-memory file formats, better storage. So if you're not as familiar with infrastructure, generally just know SSDs are better, and just knowing other, applying some of the things that you understand about training models, like pre-batching your models can also help, as well as just pre-caching the results. So if you want to increase the efficiency of your training, one thing you could do beforehand is, rather than rerunning the same ETL process every time, just save your just run it once and then pre-save your ndarrays. That will increase your training. That will decrease your training time by quite a bit. So just understanding those things can also, I think, help you optimize your ML experiments as well. Faster models, something to think about is something called data precision. So numpy, for example, generally, and TensorFlow, among other things, tends to default their data type to float 64. So if you're a Java developer, you might know double. Float 64 just means that it takes up more RAM, but can represent more values. So precision is a fairly common. That's actually one of the first things you typically do when you optimize a model. You change it to something. You change it to something with less precision, which means that it's less capable of expressing values in floating point. That can affect your training results. So you may not. You may want to make sure that you apply specific optimizations. Like mixed precision training is fairly common now. But either way, you should always look at the data type first. Like, what data type is my model? What does it expect? Can I change it to be something more efficient? Because models, when they're training, need precision, but not as much when you're working with inference. As long as the results look the same, and it basically, like, if you compress the values of all your parameters to ints, then not only can your models be faster, like they execute faster, but they also just take up less disk of RAM. Data layout. So something that people may not be familiar with is that CPUs, for example, typically use something called channels first layout, which means that when I talk about channels, I mean RGB. These is the most common thing. So you have your three channels, RG and B. Depending on how you lay out your image, CPUs are, the CPU libraries are actually faster at this with that layout. So what will happen behind the scenes is that you'll actually convert your model to NCHW or NHWC for GPU. So so that's actually why, for example, TensorFlow itself actually last I knew, does not support NCHW layout for training models. So if you use keras, you use channels last by default. So of note is keras, when it had a Theano backend, started with channels first, and then we kind of switch that later. So just the way your data is laid out can also affect your performance. So in your model, so some a common optimization people might do that's fairly naive but simple to do and increases, gives you outsized gains. It's just changing the layout. Very simple. So the frameworks do this for you, but not all tools might. So just knowing the fundamentals, I think, is useful for a lot of people. So removing redundant layers. So it turns out that there's actually a lot of, there's actually various operations in graphs that are not relevant for everything. So if you remove them, they don't affect your results. And that's always kind of the key of model optimization, is just making sure that it outputs the intended result. So like if you train a model to predict dogs and cats, as long as it still predicts the right labels, why do you care how big it is? Why do you care if it executes an identity op or something redundant? So you may do layer pruning is what it's called. So you remove redundant layers and maybe you replace them with, one operation that does the same thing. Maybe you replace it with an approximate result. So that's a fairly common, so graph manipulation is fairly common and I think becoming slowly more mainstream, but again, still taking time to kind of propagate to the masses. Model size, so intuitively, if you have less numbers, it takes less space. It also takes less compute time. Of note, though, you may combine that with, say, less precision, ants, for example. So if you just decrease the number of parameters and decrease the precision, you increase your model's performance by quite a bit. And again, formats. So when I talk about formats, I mean model file formats like TensorFlow Lite, torchscript. There's all sorts of things you may convert your model to make it more efficient to perform inference and run in production. And so what that does is that allows you to execute on different platforms. So it's fairly common to have to convert your models nowadays to something that runs on specific hardware, is intended for specific performance, like footprints, like smaller devices, bigger devices. So what's actually happening there? Well, it turns out that frameworks basically implement something called a kernel. A kernel is like a convolution operation. It could be mean calculation, add, element-wise multiply, all sorts of things. So what you do is some platforms may implement these things faster than others, and those platforms generally expect a specific format for conversion. So what you'll do is you take whatever framework you use to train your model. You take the model file, like the keras output file or the hdf5 file, and you convert that to another file format, like torchscript or TensorFlow Lite or various file formats. So if you start to think of frameworks in terms of execution engines, which is optimized add, matrix multiply, what have you, and file formats, then all of a sudden you realize they all execute the same math. Understanding what a framework will run my model faster can also help when doing production deployment. So tools and techniques, so this is probably the thing most people are waiting for. So quantization is one of the first things you can Google search. That's the idea of converting floats to ints, as I already mentioned. Knowledge distillation. So this one's a little harder to pull off, not as common yet, but basically you basically train a smaller model to imitate a bigger one. So the loss function of the model that you're kind of imitating is based on the output of a bigger model, basically a student teacher. I already mentioned pruning, removing redundant layers, batch norm folding. So if you're not familiar with batch norm, it's basically, you have a model, you have an activation that's very big. You take it and you basically perform zero mean unit variance on a model activation itself. So what you can do is you can actually, but what happens when you have batch norm is you can actually take out the batch norm layer and just basically apply directly its statistics. So batch norm layers always has statistics attached, like its mean and its variance. And so what you want to do, okay, sorry about that. So what you may want to do with batch norm is you may just want to directly take the statistics out and apply that to the model itself. And so what you do is you reduce a lot of redundant calculations by doing that. And finally, fully connected layers decomposition, which means you basically take the model and figure out a way to remove the connected layers. I already mentioned optimized data format. So you might convert your data to something more efficient, like Apache Arrow or what have you. There's a lot of ways to convert your data. I won't talk about all of them here. And overall, as I mentioned, sorry, there's a little bit of redundancy there. At the end, minimize communication overhead. So as I mentioned, your whole pipeline matters. So if you can make interaction with your GPU more efficient by batching your data better. So imagine you have a camera and you're sending data to the GPU. There's going to be latency because the camera needs to download the data to the CPU, load it, do all sorts of things, and then your camera has a certain number of frames per second. You need to convert that to an image for analysis. All that whole end-to-end pipeline, if you can optimize that and make it more efficient with the GPU, then your overall latency will be faster, like your recognitions per second or what have you for your use case. And as I mentioned earlier, with your data compute, make sure that your data storage, wherever it may be, is close to your compute. So tools, there's a few that I want to call out. One is a category called deep learning compilers. This is a fairly new concept. So imagine you have a graph that you saved, like you have a model file that you saved. What you might want to do is then compile that model to something more optimized. So what does a deep learning compiler do? Well, you tell it which hardware you want to run on, and it figures out the best way to execute, like, as I mentioned, deep learning frameworks are basically kernels, which are, fast math operations, plus, a layout, a graph configuration, like like add is add is X and Y combined together to get Z. That's a graph, right? So it will figure out ways to optimize that graph structure as well as the, which kernel should I use? So for example, NVIDIA implements a faster kernel for convolutions than maybe the default framework does. So what a compiler might do is look at that and say, oh, it's using the default one. Let me switch in the NVIDIA one instead. So compilers will do all sorts of things to kind of transform your graph to be optimal for a given configuration. Something to note though, these things are not ready for production yet. So an example like TVM, if you give it a model, what it will do is literally a brute force search to find, it will attempt to execute something, see how fast it is, and then from there be like, oh, well, this this will run faster on ARM, this will run faster on GPUs, what have you. So that search will take 12 hours sometimes. And of note is it mainly works best with ONNX right now. So a lot of things I think are kind of targeting ONNX now. Glow, this is from Facebook. TVM is from the Apache Foundation. Glow is from Facebook. It's mainly focused on PyTorch models, and they focus on simpler optimizations, like batch pruning, like pruning layers, etc. And MLIR is an integration with LLVM, so it's literally the fusion of a compiler with deep learning specific text. So it actually emits LLVM IR. So if you're not familiar with LLVM, it's basically the compiler you see a lot nowadays on like very big on Apple computer, for example. So LLVM is also more liberally licensed, so it has kind of its own backing, and it's meant to be a competitor to GCC. So in general, so LLVM has this idea of a backend, so you can actually get it to, or a front end, so you can actually get it to kind of emit LLVM IR, which then, then runs faster math kernels, is kind of the idea, benefiting from compiler optimizations innovations. So, compiler people are just focused on performance. Simplify is something for, I'm aware of the time, by the way, so I'll finish up here. So simplify is for, simpler optimizations as well as tf optimize, which focuses on graph optimizations. There's vendor specific ones like TensorRT and faster AI for the same kinds of things. And that will wrap up my talk.